In the grand theater of the cosmos, the death of a giant marks the birth of an unthinkable monster. When a massive star, holding between 7 and 20 times the mass of our own sun, runs out of its nuclear fuel, it can no longer fight the crushing grip of its own gravity. In a fraction of a second, the entire star collapses under its own immense weight, crushing its core with catastrophic fury and triggering a brilliant supernova explosion. While the outer layers are violently blasted away into the deep dark, a silent, ultra-dense heart remains. This is the genesis of a neutron star, a remnant born from the ultimate cosmic destruction. To truly comprehend the extreme physics of this newborn titan, we must look at its mind-bending scale. Imagine a sphere so small it could fit comfortably within the boundaries of a human city, spanning only about 15 miles across. Yet, squeezed inside this city-sized volume is the crushing mass of up to 2 entire suns. This creates the highest stable densities known anywhere in the observable universe. If you could scoop up just a single teaspoon of this exotic stellar material, it would weigh more than Mount Everest. It is a world where nature packs an entire star into a local neighborhood. What happens to the hearts of these dead giants when they are pushed to the absolute brink of becoming black holes? Matter at the heart of a neutron star, the crushed remnant of a massive sun, is on the brink of becoming a black hole. For decades, scientists have wondered about the exact properties of this ultra-dense matter, the most compressed material in the measurable universe. When a massive star's fuel runs out and its core collapses, protons and electrons are violently crushed together to form a dense matrix of pure neutrons, releasing tiny neutrinos that escape into the void. At the center, matter is packed to twice the density of an atomic nucleus, all compressed into a city-sized sphere. But a fundamental question remains: how squeezable is this forbidden interior? In some theories, the extreme pressure breaks neutrons apart into a fluid sea of even tinier particles called quarks, resulting in a smaller, squishy core. In other models, the neutrons hold their ground, resisting the collapse to create a larger, stiffer star. Scientists used NICER's precise measurements of 2 pulsars to narrow down how compressible these objects are. A pulsar is so dense that its intense gravity severely warps nearby spacetime, bending light rays from its far side directly into our line of sight. This dramatic distortion acts as a cosmic lens, making the star look significantly bigger than it actually is. The more massive the pulsar, the greater the warping, and the larger it appears to our eyes. To test these limits, NASA's NICER telescope turned its gaze toward J0740, the heaviest known pulsar, packing over 2 times the sun's mass into a space just 16 miles across. By tracking how its intense gravity warps nearby spacetime, allowing us to see X-ray emitting hotspots on its far side. NICER revealed something extraordinary. The data disfavors both extremes, challenging old theories and forcing physicists to draft entirely new models where neutrons and quarks must coexist. It is a brilliant reminder that at the final boundary of stable reality, nature forms a magnificent masterpiece, short of absolute oblivion. High above Earth, NASA's NICER telescope scans the cosmos from the International Space Station, unlocking the ultimate secrets of extreme matter. A pulsar is a type of rapidly spinning neutron star, the crushed, city-sized core left behind by a supernova explosion. Located 6,500 light-years away in the Crab Nebula, one famous pulsar spins 30 times a second, flashing as one of the brightest objects in our sky. Its whirling magnetic field unleashes intense beams of radio, visible light, X-rays, and gamma rays. It is one of only a few that emit sporadic, unpredictable giant radio pulses, hundreds of times brighter than its regular emissions. Now, through the eyes of NASA's NICER telescope, scientists have discovered a sudden 4% surge in X-rays, synchronized with these giant pulses. Because X-rays pack millions of times the punch of radio waves, this modest boost reveals that these eruptions release dozens to hundreds of times more energy than we ever suspected, rewriting our understanding of pulsar behavior. But these cosmic lighthouses do not always wander the wilderness of space alone. Analyzing data from the NICER mission, astronomers uncovered a record-shattering celestial pair locked in a relentless gravitational embrace. In a binary system called IGR J17062, a super-dense pulsar and a lightweight white dwarf companion revolve around each other every 38 minutes, the shortest known orbital period for this class of system. Separated by just 186,000 miles, a distance less than that between Earth and the Moon, the companion star whirls around its heavy partner. Yet, NICER's instruments are so sensitive, they detect slight fluctuations in the pulsar's X-ray emission. Catching the tiny gravitational tug of its companion and proving that even the most extreme monsters follow the ultimate clockwork of gravity. But the galactic wilderness holds an even more terrifying evolution of these dense spheres, the magnetars. Boasting the strongest magnetic fields known in the cosmos, up to 10 trillion times the strength of a refrigerator magnet. These city-sized titans are defined by pure, magnetic, volatile power. Through the unblinking gaze of NASA's NICER telescope, scientists examined a shifting landscape on a magnetar cataloged as SGR 1830. Rotating every 10.4 seconds, its surface exhibited 3 multi-million-degree X-ray hotspots drifting across the crust. For the first time in astronomical history, we witnessed these thermal regions slowly merge together, accompanied by dozens of powerful, unpredictable X-ray bursts rippling across the star's hypermagnetized surface. In April 2020, a high-energy blast of X-rays and gamma rays swept through space, triggering sensors across multiple spacecraft. Lasting only the blink of an eye, this eruption unmasked the terrifying power of supermagnetized objects called magnetars. Part of the Neutron star family, the crushed, leftover cores of exploded giants, these city-sized remnants possess magnetic fields up to 1,000 times stronger than a typical neutron star's. Sudden reconfigurations in this ultra-strong field drive brief, apocalyptic outbursts known as giant flares, capable of altering Earth's upper atmosphere from tens of thousands of light years away. On April 15th, an international fleet of spacecraft, including NASA's Fermi, Swift, Mars Odyssey, and Wind, alongside Europe's Integral satellite, picked up the rapid surge. By calculating the signal's precise arrival times across these distant missions, astronomers pinned the blast directly to the disk of NGC 253, a bright nearby spiral galaxy. From start to finish, the entire colossal event lasted a mere 140 milliseconds, as fast as a single finger snap. While astronomers detect cosmic gamma-ray bursts, or GRBs, almost daily, this April blast posed a unique puzzle. It initially resembled a short GRB, events typically triggered by merging neutron stars more than 100 million light-years away. However, a genuine short GRB, located in our own galactic neighborhood, should have appeared blindingly bright. Detailed exploration revealed that this outburst was not a distant merger, but a rare magnetar giant flare, brilliantly masquerading as a short GRB. Previously, astronomers recorded only 3 giant flares closer to home, each displaying a characteristic spiky tail as the flare's hotspot spun in and out of view like a lighthouse beam. While this spinning signature is too faint to detect across millions of light-years, the star's unmatched, extremely fast rise in brightness set it apart. Now, the precise localization of this 2020 event to the disk of the Sculptor galaxy has finally unmasked the truth. Astronomers now suspect that a small percentage of observed short GRBs are actually giant flares, high-powered eruptions triggered by the strongest magnets in the cosmos. When super-dense neutron stars crash, the cataclysm ripples across the entire cosmos. These city-sized remnants will eventually merge, blasting gamma rays, warping space-time, and leaving behind a black hole. To detect these extreme systems long before they collide, new simulations are now guiding the way. Run on NASA Ames Pleiades supercomputer. These models show how their super strong magnetic fields interact long before the crash. As the fields intertwine, they produce a distinctive glow that intensifies as the stars spiral closer together, helping next-generation telescopes predict imminent stellar collisions. When the final plunge occurs, the merger creates a flash so violent it rattles the very fabric of reality. In 2015, waves of cosmic energy traveling for more than 1 billion years gently shook space-time in the vicinity of Earth, captured for the first time by the LIGO observatories. Near the colliding masses, extreme curvatures of space-time bend reality, while expanding purple ripples represent distortions spreading outward as gravitational waves. Less than half a second later, NASA's Fermi Space Telescope picked up a brief flash of high-energy light from the exact same region. By matching light with space-time ripples through this multi-messenger astronomy, scientists can dramatically narrow down our search areas, opening a pristine new window into how the universe works. Because a neutron star packs such an immense mass into a tiny area, it warps the geometric fabric of reality itself. According to Einstein's general relativity, its extreme gravity bends space-time into a deep gravitational well. As light from distant background stars passes near a neutron star, the rays are forced to travel along this curved fabric, creating a spectacular visual phenomenon called gravitational lensing. This warp is so severe that it bends light from the far side of the star around to the front, allowing us to see portions of its back surface simultaneously. It is a place where reality is visually turned inside out. Standing at the absolute limit of physics, a neutron star balances on the edge of complete oblivion. It is the last stable stop before total gravitational collapse. If a neutron star feeds on a neighboring sun and gains just a fraction more mass, it crosses the absolute threshold of stability. The interior forces can no longer resist the crushing weight, and the entire sphere collapses inward, tearing a permanent hole in reality to become a black hole. Yet for this brief moment, these exotic titans endure, remnants of dead giants, cosmic lighthouses, and creators of gold, shining brightly in the grand tapestry of our eternal universe.